All right, everyone. Welcome back to the AI Research Roundup. I'm your host, Alex, and today is May 3rd, 2025. We're looking at a fascinating ICLR conference paper published just over 3 months ago, titled Capturing the Temporal Dependence of Training Data Influence. So, this paper tackles how traditional ways of measuring data influence don't really work for foundation models, because, well, the order of data matters now. They propose a new way to track this influence throughout the training process. Okay, so Figure 1 here really illustrates this temporal dependence. Part A shows the average data influence score across training batches for Pythia 410M. You can clearly see these distinct phases: a high-impact start, then a long, low-impact period, and finally, influence gradually rising again. Part B then shows that focusing data selection efforts only during those high-impact early and late phases, well, it gives nearly the same performance boost as selecting throughout. Building on that, Figure 2 provides a nice illustration of how their proposed data value embedding, or DVEmb approach, works conceptually. It shows a simple two-step training process. You see, the DVEmb vector for a training point evolves. It rotates and rescales from t = 0 to t = 1 due to subsequent training. And crucially, the influence on a test point is calculated by projecting this final embedding onto the test point's gradient vector. Okay, so Figure 3 provides some nice empirical validation for the DVEmb approach we just discussed. It directly compares their method, DVEmb, and traditional influence functions against the actual ground truth leave one out scores for an MLP. Well, you can see in plots A and C, DVEmb shows a strong correlation around 0.74. But look at plots B and D. The influence functions show almost no correlation. This really highlights how DVEmb accurately captures that trajectory-specific influence. So, we saw DVEmb is more accurate, but is it efficient? Well, Table 1 tackles exactly that, comparing DVEmb against LOGRA. Look at the peak GPU memory needed for storing the embedding data. DVEmb needs less than a gigabyte, while LOGRA requires over 63 gigabytes. And the throughput for storing? DVEmb is way faster, over 15 times faster. This really highlights the practical efficiency gains of their method for these large-scale models. Okay, so Table 1 showed us the practical speed and memory wins. Now Table 2 breaks down the theoretical complexity. It compares DVEmb and LOGRA on storage, memory, and flops. For storing the embedding data, look at the storage complexity. DVEmb scales with training iterations and batch size, while LOGRA scales with the total dataset size. This is a key theoretical advantage for DVEmb, especially with huge datasets and long training times. This underpins the efficiency we saw earlier. Okay, so Figure 12 digs a bit deeper into this approximation aspect, specifically the random projections used for efficiency. Part A shows how the Spearman correlation changes with projection dimension. You see, DVEmb consistently correlates better with the high dimension results than influence functions do, even at lower dimensions. And Part B shows this correlation is pretty stable across training epochs, so the approximation quality holds up well over time. Okay, so wrapping things up, we've seen that this data value embedding, or DVEmb approach, really captures the temporal dynamics of data influence during training, unlike older methods. And crucially, it's incredibly efficient in terms of speed and memory compared to alternatives. This gives us valuable insights and practical ways to manage data selection for foundation models. All right, that's all for this AI Research Roundup. Thanks for tuning in.